Okay, so you're all welcome to the sensor design and application in advanced manufacturing process. And today we are going to discuss at length about the types of sensors. We're also going to look at the operational principles of the sensors. And we are going to see application in manufacturing this industry, as well as looking into the trends and challenges associated with using these sensors. And we will go into as well the question and answer discussion at the end of it all. So without wasting much time, we will like to go over to the next slide, which asks directly the question what sensor is all about. And for us to know, looking at the block diagram here presented, sensors are devices that detect and respond to input from the environment. And these inputs from the environment can be in the form of temperature, it can be in the form of pressure, it can be in the form of light. And what sensors does is that they just sense these physical inputs. Although they cannot by themselves work alone, they require transducers or transmitter in order to convert this detected signal into a readable signal, such as electrical signal. It could be digital, it could be visual. And sensors in a whole, the purpose of which is they allow machines and systems to take a complete care of themselves without human intervention. We are going to look at their role also in manufacturing. Sensors make it possible for machines to work without human input, like I said earlier, when it comes to playing the automation part of the role, and they detect conditions and trigger certain functions. And in real-time monitoring, the variables such as the temperature, pressure, and motions are also continuously tracked for immediate response. And they are very effective for safety and efficiencies. It helps to detect malfunction early enough and reduce human error and optimizes the process, the production process to continue. You can take a look at the benefit from this short video clip, how sensors are being used in the manufacturing industries. Here, a retroreflective sensor, for example, in this case, whereby it can be used in numbering or counting the number of cans passing through the conveyors. You can see this is done independently without human intervention. Carrying out the real-time monitoring, and it's more effective. It's giving the on signal, which goes directly to the programmable logic controllers. I pause briefly from there just to give an overview of what sensor does in industries. We go over to the classification of sensors. Sensors are being classified based on what the properties they measure. Could be they measure temperature, they measure pressure, proximity, light, vibration, flow. There are a lot of different types of it. So we look at their classification based on the properties these sensors measure. We also classify them based on the output type they offer. If the output of the sensor is analog, then we can call it, okay, it's an analog sensor. If it is a digital, we classify it also as a digital sensor. Then we also go into contact. We classify them by contact. Are the contact-based sensors that which you have a direct physical touch before they respond to an output, or non-contact sensors? These are three different ways which we classify them. And if you look at here, we have a lot of types of sensors shown here. like the air pressure sensors, humidity sensors, alcohol sensors. There are numerous types of sensors here shown. And we are not going to discuss so much into all of these kind of sensors. We are not going to talk about all of them. We will only pick some to discuss more about it, just perhaps one to dive more into it, and that has to do with pressure sensor. But before we discuss what pressure sensor is, we will like to know what pressure is. Pressure is an expression of force exerted on a surface per unit area. And we commonly measure pressure of liquid, air, and gas, among the other things. The standard unit for pressure is the Pascal, and this is equivalent to 1 Newton per meter square. Among the well-known standard for measuring pressure is bar, and PSI also, which is well known among people living in the United States. The pressure of an air, for example, in this next slide, in your vehicle tire is a great example of pressure and how it is measured. As we air the tire up, the force exerted inside the tire increases, causing the tire to inflate. And this is monitored with a pressure sensor inside the tire for most vehicle types. So, how does pressure sensor really work? Look at this next slide. You can see, in a nutshell, what it does is that it converts the pressure to a small electrical signal, which is being transmitted to the PLC via the input card of the controller. And for this same purpose, it is also called a transmitter. And the two basic types of signal used during the transmission are 4 to 20 milliamps or 0 to 5 volts, depending. Most pressure sensors function using piezoelectric effects. And that takes us to the next slide. This is when a material creates electric charge in response to stress. And the stress can be pressure, usually pressure, in this case, for pressure sensor, which can also be due to bending, it can be twisting, it can be vibrations. And the pressure sensor detects the pressure, and then it can determine the amount of pressure by measuring the amount of the electric charge directly here. And going more into what piezoelectric effect is, in 18th century, precisely 1880, it was discovered that certain crystal materials such as quartz, Rochelle salt, and many others generate electrical charge when subjected to pressure. That effect was named piezoelectricity, derived from a Greek name piezen, meaning to press. So these crystals, in their natural form, are integrated in the designs of pressure sensors, such that when the sensor detects a force per unit area, which is pressure, this pressure can be in the form of maybe gas, it can be in the form of liquid, it can be also in the form of mechanical stress, like I pointed before. It can be in the form of vibration. The pressure makes the piezoelectric material inside the sensor to deform slightly, causing displacement of electric charge within the crystal structure, leading to a net electric polarization. That displacement or the displaced electric charge are then seen across electrodes that are attached in the crystal then creating a measurable voltage, which is proportional to the applied pressure, just like here shown. From the hammer here, you can find from here the hammer here, and this is the quartz. And then when force is being applied directly here, it creates electric charges, which can be seen across the connected, which is connected, and then it can be measured directly with a voltmeter or thereabout. So that we can go to the next. Sorry about my drawing. I hope I'm being heard clearly. I hope.
Yeah. Please go ahead.
Sure. Good. So going over to the next slide, we see we have three common pressure sensors or pressure that can be measured with pressure sensors in industry, commonly measured in industries. And those pressures are first gauge pressure measurements. We also carry out oftentimes absolute pressure measurements in the industry. We also carry out differential pressure measurements in the industries. And regarding the gauge pressure measurement, first of all, here we measure the reference with reference to atmospheric pressure. Atmospheric pressure, it's usually a standard of approximately 14.7 psi. And where we have a positive pressure value, then a positive pressure value means that we are measuring a value above atmospheric pressure. And value below 14.7 psi indicates that we are measuring less than atmospheric pressure. And then regarding the absolute pressure, in this case, the sensor measures pressure against vacuum. Normally, a vacuum pressure is 0 psi. So if you desire to carry out measurement of a value that is less than the atmospheric pressure, so you use this kind of pressure sensor for absolute measurement. And in practice, it dictates how much vacuum or negative pressure exists in a system normally. In industries, we use this kind of one, for example, in places like where we want to extract, like in vacuum pumps. For those in the alcoholic beverage manufacturing firm, like in filling and packaging, when we, in the process of evacuating air from a returnable glass bottle or glass bottle directly, we suck all the product because the filling process doesn't have to take place alongside with air inside. So we need vacuum, and good vacuum, a negative value. So in this case, we use this kind of sensor in this application for vacuum pumps. The third type of measurement I was talking about has to do with differential pressure measurement. This one, it's clear enough in the sense that we measure the difference between two pressures, and then the reference one, as shown in the picture here, it's what is being captured. We only take measurement of two, the actual what we want to measure, and then the reference ones, then we have the value of it all. In advanced manufacturing industry, we can also look at the uses of these measurements. And that takes us to the next slide, where we have the application in boiler, for example. Here you can see just a picture indicating a boiler. Boiler is used widely in industry to provide steam to destination machines. And In this case, we can use this pressure sensor in various means. For example, you can see here, we have PS1, where we are indicating the boiler directly just to observe and view the pressure that is in the boiler itself. We also use pressure sensor in this case to indicate also the pressure. For example, if the pressure of the boiler is 12 bar, just for example, and then we are firing the boiler more without consuming what we fire. And then if the pressure is built above the required pressure inside the boiler, with the help of a pressure sensor like seen in this case now, it can send information to the programmable logic controller via the input card, informing the controller to open a safety valve, which is shown here as PRV, which is a pressure relief valve. It opens the pressure relief valve, and then with the pressure relief valve, decreases the pressure a little bit for the boiler, and then it's back to normal. This reduces accidents. So in essence, it works in the form of assisting in safety control, mitigating the risk associated with boiler or excess pressure. We also, like in the case of the third here, this third sensor here shown, it can also checkmate the volume of steam transmitted to the sent to the destination machine. Assuming the boiler is having about 8 bar, and then we are sending up to the destination machine requirement could be we say 5 bar or even a 4 bar. For example, if it is 4 or 5 bar, then with the help of this sensor, pressure sensor, we can now say to the pressure sensor, open. In addition, because it's actually not going to work alone, it's going to work alongside with other equipment such as the modulating position and modulating valve for steam. So when the pressure sensor senses steam pressure more than the required, whereas our intention is to send just about 5 bar to the destination machine, meanwhile the ability of the boiler is 8 bar. Then we can tell the controller, when you see a pressure of about 8 bar, okay, what you have to do is close the modulating valve about 75% so as to reduce the pressure of steam sent to the destination machine. This is various ways which we can actually use pressure sensors in the case of a boiler like this in industry. And we can go over to the next slide. Here, the differential pressure measurement. Here, the pressure sensor are also installed to within filters, or in order to be able to check in different forms. For example, like this picture shown here, it's a direct flow of liquid. And you can see pressure sensor in this case installed in between a strainer or maybe a filter. We check the incoming pressure in this other side, and then we also check the outgoing pressure in the other side, and then we compare the pressure. When there is a very high difference in the pressure itself, then the value of the pressure it's given to the PLC, that's a programmable logic controller, via the card, and then a little programming is already done inside, whereby with the help of that program, the sensor will be able to the sensor will be able to offer information to the programmable logic controller, and then the programmable logic controller can put a stop to the machine, thereby alerting either via the HMI that there is a filter clock in between due to the pressure difference, which is too wide among them. It's either the filter in here seen between, it's either is too much, it's clogged, or the filter is completely dirty and then it has to be replaced. This application is widely used in the like cleaning system, effluent treatment plant, and many others to checkmate pressures. We also use it, for example, in checking leakages in between tanks where there is big differences in pressure. So a small programming is done from the controller side of it, and it does these checks and transmit the information to the logic controller, where alert will be sent to the HMI operator, or the technical personnel will know exactly the current condition of the filter. Then going over here, another common use of pressure sensor is a level measurement. As shown here, basically the hydrostatic pressure measured from the sensor is being used. In manufacturing industries, this is a common and effective method for measuring the level of liquids in a tank or in vessels. The key idea is that the pressure at the bottom of a liquid column is directly proportional to the height or the level of the liquid. So for those in the filling and packaging industry, can take your mind back to machines like bottle washers and tunnel pasteurizers, or even in buffer tanks. To achieve desirable result, the pressure sensor must be mounted either at the bottom of the tank or by the side, very close to the bottom. For a vented tank, pressure gauge sensors are also used, like in the case of tunnel pasteurizers and bottle washer, which I mentioned earlier. Whereas in absolute differential, pressure sensors are also used for a close pressurized tank. Or if you want to make use of this in measuring level in the tank, what you have to do is that the density or the specific gravity of the liquid itself need to be known. That is if the liquid is not water. For water, of course, is a standard that we have already for the value for water, and then we already know the value for the acceleration due to gravity, 9.8. Then the height of the tank has to be done by measuring what it is. You physically can make measurement of the height of the tank to determine it. And that is what we commonly do by scaling. In the program part of it, we say we scale the sensor to harmonize with the physical tank, so as to use it for level measurement. So like I said earlier, there are things that can affect these ones, like the density, the type of liquid you're going to use. That is, if, for example, if it is going to be caustic or if it is going to be oil. So this need to be known. Then foam or agitation may also affect the sensor reading. Put this into your mind. That can affect sensor reading. So you have to think about how you will mitigate this, maybe by filtering excess foams or thereabout. Another thing that can affect using this can be mounting errors. If not properly mounted, then there can be possibility for bubbles or height error. And remember, like I said, it must be mounted very close to the base of the vessel. Venting also If you are using it for level measurement, you also ensure that the tank has an open end. It has a vent so as to avoid pressure build back. Okay, if you look at the next slide, you see this is just a PID drawing for a tunnel pasteurizer. And in a tunnel pasteurizer like this, from the R1H zone and down to the R1C zone, you have water in the tanks. This need to be maintained during production in industries. Same is applied to R2H to R3, R2C, and vice versa. They are recuperating each other. So in industries, we use the level sensor to ensure a stable or sustained stable and equal level in both tanks. Thereby, during production, the both pumps are running, but we want to achieve level balance in both tanks. So this is also an application of it in industry. And I will also, these are example of physical sensors. You can see example of physical sensor here used as pressure in the industry. This is a very good example. This is a deaeration tank and how sensors are being used in applied. You can see they are being connected directly with cable, which goes over to the input card and then transmit the information, like I said before, to the programmable logic controllers. So from here, the pressure, the hydrostatic nature gotten from the sensors themselves being transmitted to the programmable logic controller. The logic controller itself send and act on the information transmitted by the sensor themselves. So I go, I'm having problem a little bit with my drawings. I hope we are together.
Oh, yeah. All good.
Good. Okay. Now, I spoke about electric pressure sensor and simple designs. If you take a look at these pictures, there are example of pressure sensors, usual pressure sensors designs. And how do they really work? Here, the pressure sensor itself is screwed in the measuring points at the process connection, right inside here. And that is the step one, how it is practically being designed. And if you go to the next one, here, we have the pressure sensor elements convert the presence pressure into an electric signal. Is directly in here, the element itself. And the next picture, the next slide shows an electronic circuit. It's a conventional electronic circuit where a conditioning circuit, I will say, like an amplifier, whereby the sensor detects the information and then passes through the amplifier. The tiny voltages seen from the sensor, it's being amplified by this electronic circuit here built in. And after being amplified, it goes over to the next slide. This is being amplified and goes over, hand it over directly to these electric connectors. Usually there is a body here. A suitable case like this is just to protect it against environmental influence. And also we put into consideration different types of cases pay different types of also uses. For example, the kind of sensors we are going to use in steam boiler must be able to resist high temperature, and we have to put into consideration or factor using a case that can accommodate temperature over 150 to 200 degrees Celsius. And then for such, we also can limit the use of material towards, maybe if we are using the pressure sensor for low, let's assume for just a mere cold water or for water of a room temperature, then we may not bother much about reinforcing the suitable case part of it. This is important. And then this is how it comes to the electrical connection. And after the electrical connection side of it, it is then being protected this way with a cover. So, and then just that. So here we can see the operational principle of it all. The sensors operate in various forms in terms of resistive. It measures changes in electrical resistance. That is for pressure type, like in terms of strain gauge. And then we have capacitive. That's the operational principle of which. But for today, we only spoke about piezoelectric, and subsequently we will go over to something else. But for today, we concentrated on the operational principle of pressure sensor using piezoelectric electricity. And we have also the system being integrated in different forms. For example, sensors are very good. We use in the sense that in programmable logic controller, I've mentioned that already. We apply it in SCADA monitoring. Without the help of sensors, we cannot work without with SCADA. And also we apply it in Internet of Things and many more. And then the use case example has to do with different industries. Application in automotive assembly, you have a lot of robots working alongside with sensors for effective production. In dietary industry also, this is widely used. I make mention of storage and also pasteurization conditions that are kept correct by temperature sensors, for example. This is just to show advantage of how sensors can be in industry. And then in pharmaceutical manufacturing, many more in terms of fluid flow mixing and sterilization and many more. We have level sensors and pressure sensors like what we have discussed today. So the use cases are so huge in various industries. The trends and the innovations are varied. Presently, we have a lot of sensors that are smart sensors. There are even self-diagnostic sensors, many of which, and some have the ability to communicate directly to the controllers themselves because they are smart sensors. We have wireless technologies, a lot of which are now more available. And then the advantage is that this kind of one, they reduce the wiring cost and also they reduce complexity. Installations in remote and rotating equipment are also advantageous when it comes to wireless technology sensor application. We install some of them in rotating machines where a normal standard wired sensors cannot be possible to fit in such places. AI and predictive maintenance. These sensors are also able to predict the failure based on sensor data. They can predict their own failure. And also they help in minimizing downtime and also minimize maintenance costs. This is a lot of great advantage and the innovation in the sector of sensors. However, it goes with challenges. And among the challenges are heat, environmental factor, like harsh environments, where you have a lot of heat, where you have also a lot of moisture. How to manage this poses a lot of challenge, like dust and many more, because these can practically shorten the life and reliability of these sensors themselves. And secondly, another challenge, calibration and accuracy. There is always a need for every of these sensor, like the pressure sensor, what I mentioned before, to be calibrated. Usually it is a job of just being done by the technician or by the technician. Usually it is just like a span and a zero and span calibration, or what I can call maximum and minimum calibration, for you to help the sensor to know its own accuracy perfectly and to carry out their measurement perfectly. So this calibration varies per manufacturers. Most manufacturers, they offer the instructions on how you have to carry it out. Some are quite complex and some are less complex. So these pose challenges, and then you have to try to ensure you have precise reading during calibration of these sensors, because the improper data can come as a result of poor calibration of the sensors. And for the other one, when it comes to cybersecurity risk, most especially when it comes to the smart sensors, they can pose security risk. They are vulnerable to attack and security breaches. So these are also things, are part of the challenges associated with sensors, with these sensors. Then in conclusion, I will say that modern manufacturing processes are really not possible without the help of sensors. It is practically not possible. This is clear and accepted. All industries, they need sensor in all sector of the industry, whether different kind of sensors. And then the process of sensor design for different measurement types and environment also differs. So we spoke already about the principle behind it: capacitive, resistive, and piezoelectric. And sensors have a lot of wide application when it comes to integrating it to programmable logic controllers, also with SCADA and Internet of Things. Then when you are selecting, or the choice of your sensor also matters a lot. So selecting the proper sensor also can help increase your efficiency and safety, as well as reliability. So we can see in an overview how valid and good sensors is in industry. And I will pause for now, and like I said at the outcome, that I will stop for a Q&A. It shouldn't be just me alone talking. I will also like to hear from your side.